Hey, welcome to The Explainer. We love to break down really big topics here. And today, we're diving into this hidden force that's literally powering our entire world, electrochemistry.
We've all got one of these in our pockets. But have you ever really stopped to wonder what's going on inside your phone's battery? I mean, what is this invisible process that lets it store up energy and then just release it whenever you need it? Well, that's exactly what we're going to uncover.
Okay, so to get what's happening in that battery, we need to pull back the curtain on the big secret of electrochemistry. And it's all about something I like to call the electron dance.
So at its very heart, electrochemistry is basically a two-way street. On one side, you have chemical reactions that can actually create electricity. Think about that battery again. And on the other side, you can use electricity to make chemical reactions happen.
And the real secret sauce to this whole thing is a process called a redox reaction. And yeah, that name is kind of just a mashup of reduction and oxidation, which perfectly describes what's going on. It's all about the transfer of these teeny tiny particles called electrons. This is our electron dance.
So check this out. The dance itself is actually super simple. You just need two partners. You've got one substance that loses electrons, we call that oxidation, and then you have another substance that gains those electrons, and that's reduction. The key thing to remember is they always, and I mean always, happen together. And hey, here's a great little trick to remember it. Oil reg. Oxidation is loss, reduction is gain. Simple as that.
Okay, so if this electron dance is just happening naturally, you gotta wonder, right? Can we control it? Can we actually harness that flow of electrons to do something useful? And the answer is a big yes. In fact, that's pretty much how we build a battery.
And the tool we use for the job is called an electrochemical cell. You can think of it as a perfectly designed little stage for this dance. It encourages that redox reaction to happen, but, and this is the clever part, it forces the electrons to travel down a path that we choose. And that path? That creates an electric current.
This is just a perfect illustration of how it all works. So in a classic battery, like a Daniell cell, you've got two different metals. At one end, the anode, that's zinc in this case, oxidation happens. It gives up its electrons. But those electrons can't just teleport to the other side. Nope, they have to travel through a wire. And hey, that's our chance to power something, like a light bulb. Then they finally arrive at the other end, the cathode. Here, it's copper, where reduction happens, and boom, the circuit is complete.
So here's the really crucial thing to get. This flow of electrons can happen completely on its own. It's what we call a spontaneous reaction. But as we're about to see, that spontaneousness is a total double-edged sword. It can be incredibly useful, but it can also be pretty destructive. And this really shows you the two sides of that coin. On one hand, you've got a battery. It's nothing more than a controlled, desirable, spontaneous redox reaction that we use to get power. But then you look at the other side, corrosion, rust. It's the exact same principle. It's just an unwanted spontaneous redox reaction where iron loses its electrons to the oxygen in the air and it just degrades. Same dance, totally different outcomes.
Okay, this all leads to a really cool idea. We know some of these reactions just happen on their own, right? They're spontaneous, but what if we want to make a reaction happen that doesn't want to? What if we could actually force that electron dance to go backwards?
Well, it turns out we can. And the process is called electrolysis. It's exactly what it sounds like. We use an external electric current, like a power source, to literally drive a chemical reaction that would not happen on its own. We are literally pushing the electrons back in the other direction.
This table just lays it all out so clearly. You have a battery, which is a voltaic cell. That takes a spontaneous chemical reaction and turns it into electrical energy. An electrolytic cell, it does the complete opposite. It uses electrical energy to force a non-spontaneous reaction to happen. And that's how we do amazing things like create pure aluminum from its ore, or get chlorine gas from something as simple as salt water.
All right, so we've seen how we can harness this dance, how we can even reverse it. But the crazy part is, this invisible flow of electrons isn't just happening in our batteries and factories. It is, and I mean this quite literally everywhere. It's shaping the world around us, and even the world inside of us.
I mean, this is so much more than just some abstract science class topic. This electron dance is what powers our world through batteries and fuel cells. It's how we produce the aluminum for our cars and cans, and how we protect giant ships from turning into rust buckets. It's the science behind a diabetic's glucose meter. And get this, it's even happening in nature. Think about photosynthesis, a plant turning sunlight into energy. And it's even how the nerve impulses are firing through your body, letting you listen to me right now. So, from the phone that's probably in your hand right now to the actual thoughts firing in your brain, electrochemistry is this incredible, hidden, fundamental force. And that really leaves us with one final big question. As we get better and better at understanding and controlling this invisible dance of electrons, what's next? What new technologies, what new cures, what new possibilities is it going to power?